Okay, welcome back to the lectures on Laplace transform, and in the last lecture we have discussed various properties of Laplace transform, and today we will continue with first with the inverse Laplace transform, and then we will evaluate Laplace transform of various special functions that appear in application. Okay, so we first define this inverse Laplace transform. Inverse Laplace transform. So, if the Laplace of f t is f s, then the inverse Laplace transform is defined as the Laplace inverse of f s as f t. Okay, now the natural question arises, that is the Laplace transform unique, or the inverse Laplace transform is unique. So, to answer this, first let me consider a function g t, which is defined as follows. It is 1 at t is equal to 1 and the value is sin t otherwise. So, at all other point it is sin t, and at t is equal to 1 the value of this function is 1. Now, in this case what will be the Laplace transform of g t, and this is again, if we integrate 0 to infinity minus s t sin t dt. So, this 1 will not influence that integral. So, we will get simply this s square plus 1, which is the Laplace transform of sin t. So, what we see from here, that if a function differ at finitely many points, then the Laplace transform of those functions are the same. But we have the uniqueness in the sense that corresponding to this sin t, this is the continuous function. So, the Laplace of this sin t, we have 1 over s square plus 1. So, we cannot have any other continuous function of which the Laplace transform is 1 over s square plus 1. So, we have uniqueness of this Laplace transform up to this continuity, if we assume, and this is the result also called a Lec theorem. So, that theorem says that if f and g are continuous and of exponential order, and if the Laplace of f is equal to the Laplace of g t for all s greater than s naught, then we have f t is equal to g t, then they are the same function for all t greater than 0. So, with this we can always have that if we want to get the Laplace inverse of omega over s square plus omega square, then we can simply write sin omega t, because this is the only continuous function which has this Laplace transform. And if we want to have the Laplace transform of s over s square plus omega square, we can simply write its cos omega t, because we know that Laplace of cos omega t is s over s square plus omega square. Now, this inverse Laplace transform, very similar to the Laplace transform, we have all those properties like linearity. So, this linearity property says that the Laplace of a 1 and f 1 s, some function, or the Laplace of the f 1 t function, let us assume is f 1 s, and the Laplace of f2 t function is f2s, and then this is a1 and the Laplace inverse of f1s. So, this is ft we can also write, and the Laplace inverse of f2s. So, this we can write f2t, this we can also write f1t. So, this is the same result what we had for the Laplace transform, because the Laplace of, if we take this to the right side, this is Laplace of a1 f1t plus a2 f2t, and that is just due to the linearity. We have a1 Laplace of f1 plus a2 Laplace of f2t. So, it is the same result what we had in Laplace transform. So, like the other properties, we have first shifting property. We will not discuss all of them again, because they are the same basically. Like here we see now shifting property. So, what this property says, that if the Laplace inverse of f(s) is f(t), so there we had Laplace of f(t) is f(s), and then the Laplace inverse of f(s minus a) is E(a)t f(t). So, this theorem was that the Laplace of E(a)t f(t) is f(s minus a). So, it is the same result. So, we have all other properties holds here in case of the inverse transform what we had for the Laplace transform. So, let us just go for the one example. The Laplace of 1 over s plus 1 whole square with this property. So, we have Laplace of 1 over s minus 1 we can write of square, and this result says that e power minus t, so a t, and the Laplace inverse of 1 over s square, and the Laplace inverse of 1 over s square is t, because Laplace of t was 1 over s square. So, we have t e power minus t. Now, I should just mention one point, that the effective method for finding a inverse Laplace transform is to construct a table for the Laplace transform and then use this table to get the inverse Laplace transform. Okay, so we go for the special functions to get this Laplace transform of this special function. The example 1, we have the Laplace of error function of square root t. So, this error function appears in probability statistics, also in PDEs and various other branches of engineering and science. So, what we have the error function of square root t, it is defined as follows. It is 2 over square root pi, this factor, and integral 0 to square root t. So, we have here square root t, then this integral will go from 0 to square root t and e minus x square dx. Yeah, this is the definition of error function. Now, if you want to take the Laplace transform of this error function, so we apply the definition. 2 over square root pi factor will come from here. We have 0 to infinity and this function 0 to square root t e minus s t from the Laplace, this kernel e minus x square and dx dt. Now, we need to change the order of integration. So, changing the order of integration. So, what we have basically, this is, if we have t, this is x, then we have something like this. It is x is square root t is the limit for x, this is for the t. So, t is from 0 to infinity and the x was 0 to this square root t. So, in fact, this will go like this. So, now we want to have this change of order of this integration. That means, now we want here dt dx. So, now let us fix the limit for the x now. So, it will go for 0 to infinity, and now for the t limits. So, we have this point to infinity. So, the upper is infinity, and from this curve to infinity we have for the t it is x square. So, the limits goes from x square to infinity for the t, and we have e power minus s t and e minus x square. So, now we can integrate this e power minus s t, the inner integral. So, 0 to infinity e minus x square we take as it is, and e minus s t will be e minus s t or minus s, and as this t approaches to infinity this will be 0. So, we have the minus minus plus, and t is now x square. So, what we will get e minus s x square over s and dx. So, what we have, this is equal to 2 over square root pi, we have 1 over s, we have 0 to infinity, and we have e power minus x square is common, and then we have 1 plus s and x square and dx. So, now we take this to make the perfect square here. So, we substitute now that 1 plus s square root with x is a new variable u. So, that we have dx is 1 over 1 plus s and du. So, in that case now the error function of square root t is 2 over square root pi, we have 1 over s, we have also 1 over square root 1 plus s, we have the limits 0 to infinity, they will not change. So, e power minus u square and dx is du, this factor is already there. Now, this integral, it is a well known Gaussian integral, and if the limits are minus infinity to plus infinity, the value is square root pi, but here we have in the half range 0 to infinity. So, the value of this integral is square root pi by 2. So, this square root pi by 2 will be cancelled with this. So, what we will get 1 over s and square root 1 plus s. This is the Laplace transform of error function of t. Now, we go for a important example which will be used while solving the ordinary and partial differential equations. So, this is Laplace transform again of the error function, but with a different form, different argument here. So, k over square root t. So, this is slightly more involved. So, let us just go through with this. The Laplace transform of the error function of k over square root t, 0 infinity, we have e minus s t, and 2 over this square root pi will come from the Laplace or from this error function, and we have 0 to, the definition says 0 to this its argument. So, here k over square root t and e minus u square and du. So, this is the error function here, k over square root t, and then we have dt. So, now again we change the order of integration, and in this case we have something u is equal to this k over square root t curve, and we have u this side and t, let us say this side. So, the t is 0 to infinity, and for the u we had a 0 to this curve. Now, if we change the order of integration and we want to have dt du. So, for the u now 0 to infinity, and for the t we will go from here to this curve. So, that means k over u square. So, from 0 to k over k square, it is a square root t k over u whole square. So, k square over u square e minus s t, and we have e minus u square and dt du, and this factor 2 over pi, 2 over square root pi, 2 over square root pi will come out of the integral. So, what we have then, it is 2 over square root pi and 0 to infinity e power minus u square. So, we have the integral of this 1 over s, a minus sign will come, we can accommodate with this limits. So, while putting this 0 first, so we have 1 and minus e minus s k square over u square, and we have du. So, what we have, 2 over square root pi, 1 over s we can take again out of this integral, 0 to infinity we have, and e minus u square minus e minus u square minus s k square over u square and du. This integral, the first one we know the value, so we can get it easily, but for the second one we need to evaluate. So, let us assume that this is I s, this integral is 0 to infinity and e minus u square minus s k square over u square du. So, here the trick is that we differentiate this di s over ds. So, differentiation under the integral sign will help to get this integral value. So, with respect to s, so this is again e minus u square minus s k square u square, and with respect to s, so we will get minus k square u square, and then we have du. So, now to simplify this, we let that is square root s k over u. So, here we want to make a square and we assume that this is x, that means we have minus square root s k over u square, du is dx, differentiate dx. So, we have this, and now this di over ds will be, so we have the limits 0 to infinity, and we have e power minus u square. So, u square will be s k square over x square. So, s k square over x square, and minus this one. So, this is again x square, and now we have minus k square over u square already there. Then we have u square from here, that is square root s k with minus from this. So, dx and u square over square root s k. So, this u square gets cancelled, and this k also. So, we have k over square root s, k over square root s, and just wait a minute. So, here we have minus k square over u square, and so what we get, 0 to infinity e minus s k square over x square minus x square dx. So, minus will be, so di over ds we have with the minus sign here, and then if we take this, we get 1 minus at this point. So, we have 0 to infinity. When the limits comes, we have, for when u is 0, we get the infinity limit. So, we change the limit here and put 1 minus sign will come. So, we have minus k over square root s 0 to infinity this dx, and now note that this is again is, we have the same form, the only change is that u is changed now to x. So, we have again here the is. So, we get this differential equation which can be solved. Di over ds is equal to minus k over square root s I, and this will give us the ln I is equal to minus 2 k, the integral of this minus 2 k square root s and plus this ln c. So, I will be c e minus 2 k square root s okay. So, now we can get this constant also, because we know that I 0 is, so our I was here. So, if I 0, then we have 0 to infinity power minus u square du, and that is the Gaussian integral. So, we have 0 to infinity e minus u square du, and this is square root pi over 2. So, with this condition we get the c square root pi over 2, and this implies now this our is square root pi over 2 and e minus 2 k square root s. So, then the Laplace transform of the error function of k over square root t will be 2 over s square root pi and square root pi over 2 minus square root pi over 2 e minus 2 k square root s. So, we had here, so this was the error function, and we have 2 over square root pi sitting there 1 over s, and the integral value 0 to infinity power minus u square du will be square root pi over 2 and minus this integral we have evaluated. So, square root pi over 2 and e minus 2 k square root s. So, we simplify this. So, square root pi by 2 we take out. So, to get this Laplace of error function of k over square root t will be, so this square root pi over 2. So, we have 1 over s only here. So, we have 1 minus e minus 2 k square root s and over s. So, this is the Laplace transform of this function. So, now we come to the next function, that is the delta epsilon function, we call it. So, Laplace of the function delta epsilon t minus a. So, this is defined as follows, that the value is 0 if t is less than a, the value is 1 over epsilon if t is between a and a plus epsilon, and this is 0 if t is greater than a plus epsilon. So, what we see now, the function is 0 outside this a and a plus epsilon, and in this range a to a plus epsilon the value is 1 over epsilon. So, if you integrate this, so what we will get, this area is always 1. So, if we integrate this in any range from minus infinity to plus infinity or 0 to infinity, delta epsilon t minus a dt, this will be just 1. This is the property of this function, and if you want to get the Laplace of this function, this is 0 to infinity minus s t delta epsilon t minus a dt. So, this is a to a plus epsilon e minus s t, and we have this a to a plus epsilon, this is defined as 1 over epsilon dt. So, here minus 1 over, this will be 1 over s with minus sign. So, S epsilon and then E per minus S t, t will be replaced by A plus epsilon and the minus this lower limit. So, E minus S A. So, this we take common, E minus S A over S epsilon, and this minus we accommodate there. So, we have 1 minus E minus S epsilon. So, this is the Laplace transform of delta epsilon t minus A. And we have defined this function delta epsilon function to go to the Dirac delta function, which is which has lots of applications in physics, or unit impulse function. So, Dirac delta function, or it is also called unit impulse function. It is denoted by delta t minus A, and it can be thought basically as the limiting case of delta epsilon t minus A as epsilon approaches to 0. So, we define this delta t minus A as limit epsilon to 0 and delta epsilon t minus A. So, just remember that this delta epsilon function is defined between A and A epsilon. The height here is 1 over epsilon, and the area here, this integral over this, is always 1. So, integral 0 to infinity delta epsilon t minus A dt is always 1. So, if we take this epsilon to A, what will happen? Because this peak, we will get a peak here, because 1 over epsilon will go to infinity in that case. So, this unit impulse function or this Dirac delta function, one can think as this limiting case of this delta epsilon function, and it has following properties which can be derived with this definition itself. So, the Dirac delta function delta t minus A is defined as having the following properties. So, the first property here is that delta t minus A is 0 for all t as long as t is not is equal to A, and if we integrate from minus infinity to plus infinity, delta t minus A dt, it is directly coming from this property. So, in this case we have it is 1. So, we can also take any other range here of the integration, as long as this A is in the range of this integration, then the value is 1. And one more important property is minus infinity to plus infinity, and this f t and delta t minus A dt. So, if any continuous function is sitting here, then this value would be simply f at this A, again as long as this A is in the range of integration. So, with this property we go with the Laplace transform of Dirac delta function. Now, it is simple because we know the nice property of the Laplace transform. So, we have 0 to infinity per minus s t of this delta function. So, we have delta t minus A dt, and in this case this will be evaluated at this A simply. So, we have E minus A s. This is the Laplace transform. In a particular case, we have the Laplace transform of delta t if we put a to 0, it is 1. So, Laplace inverse of 1 is delta t, and this Laplace transform we can also calculate directly from the Laplace transform of that delta epsilon function by taking the limit as epsilon approaches to 0. So, now we go for the Laplace transform of Bessel function. Laplace transform of Bessel's function. So, let me just introduce first briefly what is the Bessel function. So, Bessel's function of order n or of first kind is defined as j and t is the sum or is 0 to infinity with r. So, r 0 to infinity minus 1 r t over 2 n plus 2 r and 1 over factorial r and gamma n plus r plus 1. This is the definition, and what exactly it is actually. So, it is a solution of the Bessel equation, the Bessel's equation of order n. Y double prime 1 over t y prime plus 1 minus n square over t square y is equal to 0. So, we will come to this point again while discussing the application of this Laplace transform for solving differential equation, and we will come to this Bessel equation. We will see this solution as a Bessel function. So, here of our interest are two functions of order 0 and 1. So, the Bessel's functions of order 0 and 1 are given as. So, we open this sum here for n 0 and 1. So, we will get j 0 t is 1 minus t square over 2 square plus t 4 2 square 4 square minus t 6 over 2 square 4 square and 6 square, and the j 1 t is t over 2 minus t cube over 2 square 4 plus t 5 2 square 4 square and 6 and so on. And it is interesting to see that if we take the derivative of this j 0 function, you will get 0, you will get minus 2 t over 2 square, that means t over 2. Here we will get again the 4 times the t cube, and this 4 will be cancelled. So, we have 2 square 4 and so on. So, the derivative of this j 0 function is minus j 1 t. So, if we know the Laplace transform of one, we can get the Laplace transform of the other one. So, as an example, we take that the find the Laplace transform of j 0 t, find Laplace transform of j 0 t and j 1 t. So, Laplace transform of j 0 t, we have the Laplace transform of 1 minus t square over 2 square plus t 4 2 square 4 square minus t 6 over 2 square 4 square 6 square and so on. So, we can take this Laplace by term as long as the this series is convergent and the series after taking the Laplace is convergent, and we will see in this case that series is convergent. So, it is safe to take this Laplace term by term in the case of this series. So, we have Laplace of 1 is 1 over s, then we have minus 1 over 2 square, Laplace of this t square is factorial 2 over s cube, and so on. So, 2 square, 4 square, then we have factorial 4 over s 5, and we have 1 over 2 square, 4 square, and 6 square, we have factorial 6 over s 7, and then we simplify this to get 1 over s 1 minus half, we will get 1 over s square. Then the next term will be 3 over 1 over 2, 3 over 4, 1 over s 4, and because 1 over s we have taken this common. So, minus 1 over 2, 3 over 4, 5 over 6, and we have 1 over s 6, and so on. And this is with the binomial series, we can write this sum as 1 over s 1 plus 1 over s square and minus half, or this is s square plus 1, and we have minus 1 there. So, we get 1 over s, we have s square plus 1 over s square minus half. So, this will be cancelled with this, and then we get 1 over square root 1 plus s square. This is the Laplace transform of J1t of order 1 of order 0, sorry, J0t. Now, if we want to get the Laplace of J1t, this is minus the Laplace of J derivative of this j with respect to t. So, minus, now we apply the derivative theorem here. So, s the Laplace transform of J0t and minus J00. So, this J00 if we put in the series here T0. So, this J00 is 1. So, this is here 1. So, we have this 1 minus minus plus, we have 1 minus s over and square root s square plus 1. This is the Laplace transform of J1t. Okay, now we come to the another important part of this lecture, and that is the convolution, and that will be very useful to get the solution of the integral or integral differential equation or integral equations where these such a convolution appear. So, let me define what is actually the convolution. So, convolution, the convolution of two given functions f t and g t is written as f convolution g. This is the notation for the convolution and is defined as or defined by the integral f, this is star g, the convolution, and this is 0 to t. So, if we have this t here 0 to t, f integrating variable f tau and g t minus tau d tau. So, this is the convolution integral. Now, it has some nice properties like the f star g is g star f. So, the convolution is symmetric. So, this is the symmetric property, and easy to see if we take this f star g. So, it is 0 to t f tau g t minus tau d tau, and if we substitute here this t minus tau to u, will get d tau is du, and then this f star g will be with minus, and this t, because when 0 this tau is 0, we have u t, and t then it's a 0, and f, this tau is t minus u, and we have g u, and this d tau is du, and this is 0 to t f t minus u g u du, and this is exactly by the definition G convolution f. So, similarly, we have the other properties of this convolution, like if we have a constant, if we multiply to the convolution, or we multiply this constant to f and then take the convolution with g, or f and multiply c to this g, it is the same for any constant. So, c is a constant. Or if we have f is convolution with g star h, it is associative property. So, we can also have the convolution first with f and g and then the convolution with h. So, this is the associative property, and finally, the distributive property, that f convolution with g plus h is equal to the f convolution with g and plus this f convolution with h. So, we have this distributive property. Now, we go to the important theorem, and that is the convolution theorem. For the Laplace. So, if this f and g are piecewise continuous on 0 infinity and of exponential order alpha, then we have the Laplace, very nice result of this convolution. F is Laplace of the convolution of f and g is simply the Laplace of f t multiplied by the Laplace of g t. So, a very important theorem, that the Laplace of the convolution is just the Laplace of f multiplied by Laplace of g. So, we take this proof now, go for the proof, and we take the Laplace of the f convolution g. By the definition, we have 0 to infinity e minus s t, and this convolution integral 0 to t 0 to t f tau g t minus tau and d tau and dt. So, this is the convolution integral here. So, we change the order of integration to simplify this, changing the order of integration. So, we have this t and tau, the t is from 0 to infinity and this tau is from 0 to t. So, we have 0 to t. Now, if we change this order of integration, so we want to have first t and then tau. So, the tau now will be 0 to infinity, and for t from this to infinity. So, this is exactly now tau to infinity, and we have e minus s t and f tau g t minus tau and dt d tau. So, if we substitute this t minus tau to u, we will get dt is equal to du. So, this Laplace of this f star g t will be 0 to infinity, and now this t tau, so u will be 0 and infinity. So, u will be also infinity here. So, e minus s t is u plus tau, we have f tau and g u, and dt is du, and then we have d tau. Now, we have 0 to infinity. For the tau, we have e minus s tau and this f tau, the inner integral 0 to infinity e minus s u and g u du, and then we have d tau. So, if we just see that this is the Laplace transform of g. So, this is the Laplace transform of g, and the remaining part in the integral e power minus s tau f tau d tau is the Laplace transform of f. So, here we get this Laplace of f star g is the Laplace of f multiplied by Laplace of g, this theorem. Now, we just look at a few examples where we can directly apply this Laplace or convolution theorem while getting the inverse Laplace transform. For example, that the Laplace transform of s over s square plus 1 whole square I want to get. Then note that the Laplace of the sin t, we know that this is 1 over s square plus 1, and we also know that the Laplace of the cos t is s over s square plus 1, s over s square plus 1. So, by the convolution theorem, using convolution theorem, what we see that the Laplace of the convolution of sin t and cos t would be Laplace of sin t, the product, and the Laplace of cos t. So, Laplace of sin t is 1 over s square plus 1, and Laplace of cos t is s over s square plus 1. That means s over s square plus 1 whole square, and this is the function we want to get the inverse. So, this implies simply that the L inverse of s over s square plus 1 whole square is the convolution of a sin t and cos t, which is given by the integral 0 to t and sin tau and cos t minus tau d tau. So, here we simplify now, it is a sin a cos b. So, we multiply by 2 and divide by half. So, we have 2 sin a cos b. So, this will be the Laplace inverse of s over s square plus 1 whole square is half 0 to t, and 2 sin a cos b sin a plus b. So, sin t plus sin a minus b. So, we get 2 tau minus t, and then we have d tau. So, we integrate this because sin t is independent of this tau. So, we take this sin t, and here the integral will give us t, plus we have sin 2 tau minus t, and this will be the half here we have with minus cos 2 tau minus t, and divide by this 2 0 t. So, we have half t sin t and we have minus 1 over 4. When we put this t, we have cos t, and minus when we put this tau 0, we have cos minus t, and that is cos t itself. So, this is simply half t sin t, and this is the Laplace inverse of s over s square plus 1 whole square. So, with the help of this convolution, we have got the Laplace inverse of this s over s square plus 1 whole square. So, if we see that this is the product of the Laplace transform of two functions. So, Laplace product of the Laplace transform, then we can apply simply this convolution theorem to get the inverse Laplace transform. So, for example, in this, so if we have find the Laplace inverse of 1 over square root s and s minus 1, then we know that the Laplace of 1 over square root t is gamma, it is minus half plus 1. So, gamma half and s half. So, square root s, and therefore, we get this Laplace inverse of 1 over square root s is 1 over, this is square root pi, 1 over square root pi and 1 over square root t. So, this one function which we can see 1 over square root s, the Laplace inverse is 1 over square root pi and 1 over square root t. Now, the other one 1 over s minus 1. So, product of two functions 1 over square root s and 1 over s minus 1, both are familiar now to us. So, because the Laplace inverse of 1 over square root s is 1 over square root pi 1 over square root t, and the other one is simple. So, we have 1 over s minus 1, and this is the Laplace transform of e power t. So, the inverse is e t, and then by the convolution theorem, so the Laplace inverse of this product s and s minus 1 we can get. So, 1 over square root pi is and 1 over square root t, that is one function, and the convolution with the Laplace inverse of the other one. So, that is the simple case we can have. So, this is equal to 1 over square root pi and the convolution integral 0 to t, and we have 1 over square root t and e or 1 over square root tau. Now, new variable we introduce here. So, tau, because the convolution we are writing. So, 1 over tau and e t minus tau. So, f t minus tau and d tau. So, now e power t, it is a constant again, we can take out of this integral. So, we get now the Laplace inverse of 1 over square root s and s minus 1 is equal to 1 over or e power t over square root pi. So, e power t we get from here, square root pi is there already, then we have 0 to t e minus tau over square root tau d tau. Now, if we substitute that u is square root tau, or that means this du is 1 over 2 square root tau d tau, then what we get? In this case, this Laplace inverse will be E t over square root pi will remain as it is, this constant factor, and then we have this 1 over square root t d tau is du. So, it is 0 to now. So, u this tau is 0, then u is also 0, but this tau is t, then u will be square root t, and we have e minus this tau is u square. So, we have u square, and then this d tau over square root tau is du and over 2. So, we have no d 2 will be multiplied here to du, because 1 over square root. So, this implies 1 over square root tau d tau is 2 du. So, this will be replaced by 2 du. So, 2 comes here, and then we have du, and this is the familiar function. We have now e t and 2 over square root pi 0 to square root t e minus u square du, and this is the error function of square root t we have introduced today itself. So, the Laplace inverse of 1 over square root s and s minus 1 will be e t and error function of this square root t. So, this is the Laplace inverse of 1 over square root s minus 1. So, in this way we can use this convolution theorem to get the Laplace inverse of the product of the functions here, and that will be simply the convolution. So, here we conclude this lecture. So, today we have evaluated this Laplace transform of some special functions like this error function, Bessel function, and also this Dirac delta function, and we shall encounter some of these functions while solving differential equations. And so, next lecture will be devoted to solving ordinary differential equations and integral equations. So, that is all for today. Thank you. Goodbye.